Alright, so in this video I'm going to start off by going through electronegativity. Now, electronegativity is the power of a nucleus to attract electrons in a covalent bond. So, what this means is, well, if you think back to GCSE, if you had a covalent bond, something like ClH, for example, it was kind of implied that the electrons were in the middle of the covalent bond. So, something like this, okay? However, this isn't necessarily true. The electrons are, well, in the covalent bond, the electrons are closer to one of the atom than the other. So, the factor that affects which side it's closer to is called electronegativity. So, the more electronegative element is the side that it will be closer to. So, in this case, I'm just telling you this now. Chlorine is the more electronegative element. So, the electrons are going to be somewhere like here. Okay, so they're going to be closer to chlorine. Okay, so it's electronegativity. It's basically just like pulling power in simple terms. Okay, however, you do need to make sure that in an exam, if they ask you for the definition of electronegativity, you don't say pulling power. Okay, now what are the factors that affect electronegativity? Well, firstly, as the atomic radius increases, the nuclear attraction decreases, so electronegativity decreases. So, if you think about it, let's say I have an atom here. Now, here I'm just going to draw the nucleus in the middle, and let's say I want to attract a covalent bond, right? Like this. Well, actually, this doesn't make any sense. Okay, like this, right? If I want to attract the covalent bond, the way to make the covalent bond closer is by having a smaller distance for it to travel from here to here, right? Because it's the positive charge of the nucleus is what attracts this bond. So if I want to attract the bond, I have to make the distance smaller, right? That has to travel. Whereas if I have another shell, then the covalent bond here has to travel a greater distance, right? So now the attraction is a bit weaker. So the electronegativity decreases now when the atom gets bigger. So as atomic radius increases, electronegativity decreases. Okay? Another thing is shielding. So here, all these electrons here and here repel these electrons. Okay? So the more electrons you have, essentially, the more repulsion you have. So here, we have one shell of repulsion and two shells of repulsion, right? So there's a strong repulsion force. However, if we got rid of this whole shell, now there's only one shell of repulsion, right? So now it's easier to attract these electrons, okay? Therefore, electronegativity is stronger when there's less shielding, okay? So when there's more shielding, there's the atom's less electronegative, okay? So as shielding increases, nuclear attraction decreases, so electronegativity decreases. One sec, I just realized it hasn't come up on the page. And as nuclear charge increases, nuclear attraction increases. Once again, hasn't showed up, one sec. So electronegativity increases. So what this refers to is essentially the nucleus, right? If you have more protons inside the nucleus, you kind of have like a stronger pulling power, okay? Because you have a greater positive charge. And so since this is more positive, it can attract these negative electrons better. Okay, that's really it. So as nuclear charge increases, electronegativity increases as well. So those are the three factors affecting electronegativity. Okay, so here we have something called the Pauling scale. And essentially this tells you like an electronegative value for each of the elements. Okay, I haven't shown all the elements here, but this is just a few. Now, electronegativity, one reason why it's useful is it actually tells you whether a bonding is going to be ionic or covalent. Okay, so I'm going to use a game of tug of war as an example of explaining this. Okay, so imagine you have two people, and we're going to call them Bob and Sarah. Okay, pulling on a rope, right? Like in tug of war. Now, let's say Bob's a lot stronger than Sarah. Okay, what happens when they start pulling? Well, eventually, Sarah's going to lose grip. So then she kind of just lets go of the rope. And now Paul has the whole rope to himself. Now, this is because Bob is a lot more stronger than Sarah, right? Okay, so if we link this back to chemistry, when you have two atoms, the natural thing that happens is that the atoms will share their electrons. However, when one atom is a lot more electronegative than the other, okay, so a lot more stronger than the other, the atom will just take both the electrons in the bond. Okay, so say for example, chlorine, right? That's got a very high value, so it's really, really strong. So if it's like this, and let's just represent its electron like that. Actually, I'm gonna put it more in the middle, like that. And let's take sodium, right? It has a value of 0.9, so it's pretty weak, right? And I'm going to represent its electron like this, okay? Now, since chlorine is a lot more stronger than sodium, what's going to happen is that both of these electrons go here, okay? And it's not even like, oh yeah, we're sharing it, but it's closer to chlorine, like we had in this case, right, HCl. No, in this case, it's so strong that sodium just lets go of it, okay? And this is what the ionic bond is. So if we draw the rest of the electrons that weren't involved in the bond, then we have our ion, our outer shell, and then this becomes like -1, and this becomes +1, right? And then we have our ionic bond, okay? So this kind of explains what we were talking about in the previous video. It links back to it, okay? So this is the explanation of it, of why ionic bonds are formed, okay? And the actual value is 1.7. So if the difference between the two atoms is more than 1.7, then it will be ionic. So in this case, we have 3 and 0.9, right? So 3 take away 0.9 is 2.1, and that's greater than 1.7. So that's why this is ionic, okay? So that's how ionic bonds are formed. Now let's pretend for a second that Bob's not a lot more stronger than Sarah, okay? He's stronger, but not by a huge amount, right? What would happen? Well, I guess the rope, well, if I actually, let me extend this rope to make it simpler. So right now they both have like an equal amount of rope, right? However, what would happen is that Bob would pull it, so then it goes that way more, right? But Sarah still has a hold on it, right? So it's something like this. Okay, so there's more rope on Bob's side now, okay, and that's because he's stronger. However, Sarah's still holding on to it, as you can see, right? So she hasn't completely let go of it, okay? And that's because she's still pretty strong, okay? Not as strong as Bob, but pretty strong, okay? And if we link this back to chemistry, if we use atoms such as chlorine and fluorine, for example, well, I'm going to represent chlorine's electron with an X, and I'm going to represent fluorine's electron with a dot, okay? Now, fluorine has a value of 4, okay, which is pretty strong. Chlorine has a value of 3, which is still pretty strong, but not as strong as fluorine, right? So these electrons here are going to move closer to fluorine, okay, like that, okay? However, it's not so strong that this is an ionic bond now, okay? It's still a covalent bond, okay, because it's still kind of being shared with chlorine. It's just that it's not as close to chlorine, okay? However, chlorine's still getting some of it, okay? It's still holding on, okay? Just not by as much, okay? It's kind of it's an uneven sharing, okay? Whereas with ionic, if you remember, like Sarah in our case, in our example, just completely let go, right? So here we haven't completely given up of the electrons, okay? We're still holding on. And that's what's caused when you have elements with different values of electronegativity, okay? Different strengths, but not so much of a strength difference that it's ionic. So if the difference in electronegativity is less than 1.7, the bond will be covalent. Now what happens when you have two atoms with the same electronegativity? For example, two chlorines. So if we go back to our example, so let's imagine Bob and Sarah are the same exact strength, right? Well, when they start pulling on the rope, since they're the same strength, the same exact strength, it doesn't go towards one side more than the other, okay? It still stays the same essentially. So this means in our example, if we have something like chlorine with chlorine, and then we draw the electrons like this, and right now it's in the middle, right? And it's going to stay in the middle, okay, essentially. So that's what happens when you have atoms with either the same electronegativity or very, very similar. So let's say carbon and hydrogen, for example, it's a common one. The electronegativity values are different, but it's not so different where it's going to tend towards one side more than the other, okay? With carbon and hydrogen, the electrons lie pretty much in the middle, okay? And that's because the difference isn't big enough to tend towards one side. So that's how electronegativity can be used to determine whether the bond is ionic or covalent. Alright, here's an exam question for you guys to try. Pause the video, try it yourselves, and play to see the answers. Okay. State the bond type in sodium oxide and the bond type in sulfur dioxide. In each case, explain the link between the bond type and the electronegativity of the elements involved. Okay, so the bond type in sodium oxide, well, I think the easiest way to do this is by looking at a periodic table. So I said in the previous video that ionic bonding is between a metal and a non-metal. And if you look at a periodic table, sodium is on the left-hand side, right? So it's a metal. And oxygen is on the right-hand side, so it's a gas, right? Or a non-metal, sorry. So since we have a metal and a non-metal, it's ionic. The explanation, however, goes back to our explanation with electronegativity. So we know that when it's ionic, it's because there's a big difference in electronegativity. Now, our value was that it's greater than 1.7. However, you don't have to mention the values, okay? You can just say big difference in electronegativity. Now, you might be thinking, why can't I just say, for explanation, that it's a metal and a non-metal? Well, the reason is that that's not really an explanation for an ionic bond. That's more so like a property, okay, that happens. And the reason why it's normally between a metal and non-metal is because of the big difference in electronegativity. Because metals tend to have a smaller value for electronegativity, and non-metals tend to have a larger value. And because of that, they have a big difference. Okay? So the metal and non-metal are consequences of the big difference. Now the bond type in sulfur dioxide, well, we have sulfur, which is a non-metal, and we have dioxide, which is oxygen, which is also a non-metal. So we have two non-metals, therefore we have a covalent bond. and this is caused because of a small difference in electronegativity. Alright? Okay, so polarity links onto electronegativity, right? So, like we said, two elements, if they have different electronegative values, the electrons tend to one side more, right? So if we had something like ClC, for example, if we look at our values, well, chlorine has a value of 3 and carbon has a value of 2.5. So that means that the electrons will tend more towards the chlorine, so somewhere here. And therefore, what polarity is about is the fact that since the electrons are closer towards the chlorine, well, it has more negative charge, right, around it. And because of this, it's kind of slightly negative. Okay, it's not fully negative because it's not an ionic bond. Okay, it's still covalent, it's still sharing the electrons, right? But because it's got more negativity, it's slightly negative. And since the carbon's lost these, well, it's giving away these electrons a little bit more. Okay, it's slightly positive, right? There's less electrons to it compared to the chlorine, so it's slightly positive. And polarity basically just refers to this. Okay, the different polarities in the molecule. So a polar covalent bond forms when the elements in the bond have different electronegativities. When a bond is a polar covalent bond, it has an unequal distribution of electrons in the bond and produces a charge separation, slightly positive and slightly negative ends. So this bond is polar, right? However, here I've said a molecule of CCl4 is non-polar. So if I draw that out, it looks like this. Okay, so I've drawn the molecule with its slight charges. Now, the reason why this molecule is non-polar is that it's symmetrical. And the reason why that's important is that, well, this charge here, the slight positive here, slight negative here, cancels out with this one here because it's symmetrical. And this one here cancels out with this one here. Okay? And overall, there's no charge left. So the whole molecule is non-polar. It has individual polar bonds, because this is a polar bond, this is a polar bond, this is a polar bond, and this is a polar bond, right? Because the electrons are closer to this side, and same thing with here, and here, and here. However, the whole molecule overall is non-polar because they cancel each other out.